hopefully finish linear regression today, which we had started last class. Before I get started, any questions from the last class? Okay, so there are a bunch of derivations today as well, but we'll not do all of them because they are all on the slides. So just for the sake of time, we'll do one of them and we'll see how much time we have. The idea is not so much to, you will probably realize that gets a bit rigorous at points. So even if you're not able to sort of do the full thing, my goal is to give you an intuition of how it works overall. And where we left last time was we had considered this simple linear regression model. We had made a very simple assumption that epsilon I are standard are mean 0 and follow a constant variance sigma square. So there is no sigma I square, it's sigma square throughout. And what we had shown was that the optimization function that we're going to solve has two parameters, beta 0, beta 1. We used what's called ordinary least squares estimate to figure out what is beta 0, beta 1. What is so ordinary about this? Why is it called OLS? What is ordinary about it? This is least squares, but it's in this setting it's also called the ordinary least squares. What is ordinary about it? What is ordinary about this? Take a guess. It's called OLS, right? I'm sure any machine learning tutorial you do will start with an OLS example. Why is it OLS? Why is it OLS? Yeah, very good. So it's the simplest, right? So it's the simplest in the sense that this is the simplest assumption that you can make, and that's what makes it ordinary, or that's what makes some models, vanilla models, like these are the simplest assumption that you will make about solving these things. That's why it's OLS. As the class progresses, we'll only have 3 weeks ballpark left. We will do some more rounds of regression where this ordinary will become partial or it will become some other fancy term, but the central premise will remain very, very similar. One way that the approach that we took here was we differentiated that function with respect to beta 0 and beta 1. And and what we did is derive the values of beta 0 and beta 1, and very quickly this beta 1 estimate looks like the covariance that you define for x and y divided by the square root of the covariance divided by the square root of the variance of x, right? So in essence what it is trying to capture, and you can see this intuitively why it should be that, is inherently what is the purpose of beta 1 is to capture this kind of relationship, and how much slope you see is a function of, in some sense, determined by how much variation you see along this axis, right? So the more variation I see, if I have a long sort of variation happening here, but not much is happening here, what would the slope be? Flat line, right? Like, very good. So flat line, right? So if there is so much happening here, but nothing happening in this direction, it would have been a flat line. And that defines why there is an inverse correlation with respect to the variance. And of course, here it's simple to see that how much y determines x, or how much x determines y is a function of, is captured in the numerator, because the tighter that relationship is, the stronger you will climb, you'll take the incline. Right? So that bottom parameter is also important, that if you're climbing things here where most of the data points are in this vicinity, where there's not much happening here but there is some variation here, it will be a straight line. But if even with this variation, if there was lot stuff which would have happened here, then of course you're going to take the incline, and that's what defines what is your beta 1. So this is beta 1, and this is beta 0. Are those are two parameters? Are those independent or are those dependent? Hmm? Intercept and slope, yeah, beta 0 and beta 1. So y is are those independent parameters or are those dependent parameters? Independent. Why independent? Okay. There are two parameters, so ideally you would want them to be independent, because otherwise why would you want to fit two different parameters? But look there. Is that independent? Hmm. Hmm. If I fix beta naught, what happens? Good question. Let's stay there. Okay, fine. So you're fixing this. You're going to fix. Okay, so this part is fixed. It becomes inclined at this point. So which is equivalent to doing what? Rotation, but it's equivalent to shifting your axis here and saying that you're now fitting a new model which has 0 intercept. Okay. However, how does that prove that beta 0 and beta 1 are independent? You're doing a totally new regression in some sense. But that's a choice you made, right? So that's a choice that you made. So independence, for proving independence, you have to start with the choice of whether I can determine what is independence actually. How do you define independence of any two random variables? Probabilistically, what is independence? For two random variables x and y, probability of, okay. So this is the definition of independence, right? If I am doing a joint, or in other words, knowing y doesn't really tell me anything about any other information about x. Is that true in this case? In the case of beta 0 and beta 1, from the way we derived this, is that true? So if you remember, first derivation that we did was for beta 1. We determined what's called beta 1 hat, which is given by xi minus x bar multiplied by yi minus y bar and divided by xi minus x bar the whole square, which is equivalent to doing sxy by sxy by sxx. And then we use that value to determine what is our beta naught, right? And beta naught has this parameter y bar minus beta 1 x bar. So in a sense, what you're doing is you're actually using the relationship between beta 0 and beta 1. There is indeed a relationship here. They are not actually independent parameters. And we'll see how can we leverage this to understand what the model is overall trying to do. Is that clear? They're not independent. Okay, so that's what the definition of the ordinary least square is. If you define sxx to be the variance, I define xyy to be the covariance, then this is simply sxy by sxx. Just be careful. Sometimes I think I'll take the square root version of this, but mostly it will be given why it's not a universal notation. So sometimes I write that as sxx square. Sometimes I write it as sxx. So just pay attention to it. There's no universal notation. That's why I can flip around. This, if you want, can be repurposed or can be rewritten in the form of correlation between x and y multiplied by sy by sx, right? So correlation between x and y is, from the last class we know, is a measure of how tight is the association between x and y. That tight association is indeed a matter again of how much variation do you see here versus how much variation you see here. The more variation you see here, it's going to get affected, the slope is going to get affected, and that's what is captured intuitively in that formula. And beta 0 of course is remains the same. Okay, so when you run this in your programming, any programming language, broadly what you're trying to get is, at each point, the reason you got this red line as the best fit, this just happened to pass through 0, but usually that won't happen in a lot of cases. I think there's a problem actually. I think the figure does not correspond to the estimate, so I will fix it, because here it seems that the intercept is 0, but the intercept actually is non-zero. But broadly, the point of this figure is to show you that these are the residuals that you're trying to minimize, and when you do a fit, you get these kind of longish form things, and unfortunately this has gotten compressed, so I will remove this and expand this. Okay, so let's look at what is reported. The first report is of residuals. The minimum residual is minus 3000, then the first quantile is minus 509, and so on. Then you have these coefficients where the intercept estimate is minus 197. The standard error is 157. There is a t value, and then there is some probability. The same thing exists for the independent variable, which is the slope. The first parameter there is the intercept. The second there is the slope. And at this point, you should, the goal to do this kind of analysis is to make sure that while I'm always able to estimate these two parameters, do they actually have statistical significance or not? So any ideas about how would you assign significance to beta 0 and beta 1? When we derived their values, we got analytical solutions to beta 0 and beta 1, right? Which means that this is a point estimate where we got beta 1 is sxy by sxx, and beta 0 is y bar minus beta 1 x bar. Why should it have a fiddling around? Like, why should it have an estimate, but why should it have a standard error associated with it? And then why should it have a t value, and then why should it have a significance? What is that stochastic part here which is forcing you to assign a significant value to it? Okay. Okay, so the null, what is your null hypothesis in this case? Which translates to what? Okay. Okay. Okay, and your alternate? Oh, sorry. Yeah. Oh, beta naught is not equal to 0. Okay. This? Okay. Everyone understands this point about why a regression is not simply a regression, but actually a test of hypothesis. The simplest hypothesis in this case is there is no relationship between x and y. But the alternate hypothesis is there is some relationship, which essentially means that, so if this is indeed the scenario, and this is where we'll end the lecture, So if you answer, if all of you can understand this, we end the lecture in the next 5 minutes. But if that is the hypothesis, what is it that we are saying about y? That is the end slide, by the way. Y is 0. Anyone else? If x naught is true means what? Oh, h naught is true. Okay, h naught is the null hypothesis is true, then y is 0. Okay, anyone else? That so we wrote. That is how we got the hypothesis. What are we saying from a experiment point of view? Which means what? I want some more. I'm looking for a particular answer based on how the experiment was done. Huh? No, I'm talking about this hypothesis, right? Like this null hypothesis. If this is your null hypothesis, how do you observe what do you expect the y observation to be? Random, okay. More? Independent? Huh. Not dependent on x, okay. Random, not dependent on x, more? From the model that we did, if we fit these two values, what do we get y to be? Recall the experiment that I talked about. Yes, good, very good, right? So what is the experiment that you're doing? You are bringing in the scale, and all I'm measuring, I go to any one of your seat, which is the seat number is your x, which is an independent variable which I can vary, so I can go to any seat that I want. There I do a measurement where I have a scale. Now the scale is so bad that all I get is random noise, which is n0 sigma square, right? That is what the linear model ideally tries to test. And whatever evidence you gather here is evidence against that null hypothesis, that no, y is not just a pure random number which follows a Gaussian distribution, but there is some meaning to it, because I can indeed learn that relationship if I do account for that there is some stuff going on, and we'll talk about what that stuff is going on, what that stuff is, and then which defines what your intercept is, and second is what does your independent variable, how much does it influence, right? So the next part of the lecture focuses on that. When we do this regression, one of the other things that I also want you to think is, we are in this world where all of this is fit on a sample population. You don't have access to the population. So if I'm interested in whether height varies as a function of age or weight, then I have already formed a null hypothesis in my mind that it doesn't. In order to really prove it or disprove it, in an ideal scenario, I would have taken the height and the weight of all the population of interest. It could be of the world, it could be of women, it could be of men, but all possible men on the earth, for example, right? Depends on what exactly my null hypothesis is. But however fine-grained I make that hypothesis that this relationship holds only in India, for example, I will have to go to each and every person who is present in India and do that measurement. Of course, that will never be possible. So what you do is you take a sample out of this, and the observation that you have in your hand is one such sample, right? If I were to go back and repeat this study, either with a similarish xi, which means that I go again and I again measure it, the issue or the stochasticity that I'm going to get is from that measurement error, right? One thing is I could change my sample and I can repeat the measurement to test whether it holds. The second thing I could do is I can go back again to the same sample and ask that, do I get the similar slope, do I get the similar yi's or not? And as we saw in very simple cases also, that will not overall happen to be true. So whatever we are trying to fit here is one such line that among the all possible lines that was possible. Because if you measured something here today and you go again tomorrow on the same individuals, this y1 will not remain y1. It will be you'll measure it as some y2 prime, some y3 prime, some y4 prime. And the implication of that is, rather than drawing, I'll just show you what the implication of that is, that among, going to jump the slides a bit. But when we're trying to learn the relationship, if we actually had access to the population, then all the measurements that we did, we could have figured out what are the right parameters to fit it. For example, in this case, I start with a population, and I now in one where I know that when I simulated my y, what was the relationship between x and y. So I know that relationship, and that's what the blue line shows. When I actually take the sample and when I go and try to fit it, this is the red line that I get. And it's different from the population line. And I repeat this multiple times, and this is what you see here. That with the same relationship, I am now simulating different observations. All possible lines that you get here are different from, or usually different from, what is the actual real relationship, which is your population. So any line that you fit, the goal is that how close is this line to that population line. And to be able to estimate that, you need a measurement error for beta 0 and beta 1, which tells you how accurate are they to the real or the population beta 0s and population beta 1s. Right? So there is some universal value of the intercept and some universal value of the slope. We cannot know it, but we know for sure that whatever we are doing is going to be an inexact measurement, that it's a sampled version of it. The goal is to be able to learn how close are we to that estimate. And to do that, we have to define certain properties of beta 1. What properties would you want to define for beta 1, which will tell you, for example, on average, how much will it change? Yeah. Why the population line will surely exist? Because the underlying idea there being that there is some universal relationship which determines your x, which determines your y, which is conditioned on x. What? Yes, so in this case, in the example that I showed you, what I did is I know the population. I know that there are 100 patients that I want to simulate. And all I'm simulating is y is, let's say, 2x plus some random noise. So I know that this slope is fixed because I fixed it when I simulated the data. Now, among this data sets, among this population, which was of 100, I cannot measure 100, so I'm only now measuring some 50 people. I take those 50 people and I estimate what is the slope that now I get. In an ideal case scenario, the slope for those 50 people should have been 2. But what that plot shows you is you will come close to 2, but you will never be exactly 2. Right? You might get lucky and you might get very close to 2. But in your real world setting, that's what you're trying to simulate as well. That when you say that, imagine you're testing a drug, right? So you have to put out this. Your background is pharmacology. Okay, fine. So you're testing. What kind of tests would you do? Some functional test. Some functional food. What kind of functional food? Therapeutic properties. Okay. So I can. This is recorded, but I can go down that route and say that you should get some herb which cures everything that's possible. There are groups in India which are trying to sort of push for that. So yeah, let's say you get a herb and you want to test whether this is interested in doing some sort of it cures some X thing. In an ideal scenario, if that is your claim that you want to make, you would want to get all people who are suffering from that ailment and then prove that it works on everyone. Of course, you cannot do that. So you start from a sample design where you design a smaller study where you can sample some of the people who are suffering from, let's say, disease A, and some people who are not suffering from it, control, and show that when you treat people The relationship that you learn gives you this difference in the effect size, or in this difference that if their weight is this X kgs, then they have this much amount of efficacy. In an ideal scenario, that population would have been your full cohort of people who suffered from that disease, which you'll never be able to capture, right? So you will report that in this sample size, this is my estimate of the slope and this is my estimate of the intercept. But how do I know, for example, that how much does it vary? How much close it is to, let's say, its true value, if that exists at all. So in your case, there is no true value because you don't know unless you go out and find out what is that true value. In this case, you did know it because I can simulate it, right? So I can simulate, and then from that pool of sample, I can just simulate, I can just subsample 50 points from the population of 100 and show what do I get overall, and that's what this experiment is for. Okay. Okay, so back to understanding the properties of beta 1. What kind of properties would you want to understand about beta 1 or beta 1 hat in particular, because that's the estimate. What properties, what statistical properties that you have studied in this class would be useful to know about beta 1? Okay, variance. How would we go about determining the variance of beta 1? Before we talk about variance, is that clear that where is the variance of beta 1 coming from? Beta 1 variance is coming from you being one of those samples which could have existed otherwise. So there is inherent stochasticity in your measurement of the slope, and that's what we would like to quantify. So let me stay here and let me give you one possible way to expand this. How would you go about estimating the variance given this is the formula of beta 1? Before variance, what is that one thing that you need for the variance? Variance of any quantity is determined by E of x, right? So the one thing that you will need is this quantity. Okay. Okay, how should we get E of beta 1? Expectation of beta 1, right? What does it inherently mean? That if I do multiple rounds of regression by, let's say, going to my experiment field and measuring the samples again and again, then this is my average slope that I would get. That's what the interpretation of E beta 1 is. How would we calculate it? Okay. Why? So I cancelled it. I can cancel it. This is what the formula is, right? I can cancel this. Y bar is constant. So this is yi times this minus y bar times sigma xi minus x bar, which is 0. Sigma xi minus x bar is 0. Right? Sigma xi is sigma xi and n times x bar, which is 0. Okay. So that's why I just wrote it to be this. Okay. From here, how do you estimate the? So beta 1 has to be a random variable, right? How do you make from here? How do you make it a random variable? We will just do this one simple derivation and then we will assume the rest of the stuff, because rest of it is slightly rigorous and a bit messy, but not hard to do. It just requires you to do a lot of not lot of, but like some rigorous thing. So we'll do it if there's time at the end, we'll do it, but this should be simple. So if you get this right, the other stuff should follow actually naturally. How do I make beta 1 a random variable? Why is it a random variable to begin with? What is a random variable? What is a random variable? What is a random variable? Yeah, yeah. So, okay, yeah. Which is not? Okay, that is correct. So it's neither random nor a variable, but what is it? That's correct. Yes, maths up, that's what it is, right? So it has to map the outcomes to the real number line. So how can we do that here? What was random to begin with when we started this equation? Yeah, the sample, right? So which means that our y was the way this was a random variable was because that's an epsilon I that we are measuring. The reason we have that epsilon I is because again we cannot measure this exactly. We make one observation and there is a measurement process involved which leads to an error. That error happens to be Gaussian distributed. Okay, so here okay, Kundan, question? Not, is this the worrying part or is this clear? Clear? Okay. So here yi is nothing but a random variable and that's where you are able to take expectation. That randomness is seeping into the randomness that you see here and the randomness that you're going to see in beta's not case as well. What I've done so far is I have this formula that we determined last time. I substituted yi to be beta naught plus beta 1 x plus epsilon I. And now I can take expectations because otherwise those expectations are a function of your actual measurements, yi, which I don't have, which I don't know. Right? I don't know those values. I know them as a function of the measurement because I've assumed that this model is correct. So if this model is correct, then yi should be a function of the randomness. That randomness comes from that measurements epsilon I, which is inducing the randomness. And now, what is this equal? How do I solve this? Okay, n times of sigma. No, this is not squared, but this is just, yeah. So I can open it up. So the way to open it up is, this is sigma, which is outside, beta 0 plus beta 1 x, sorry, xi, and epsilon I. Okay. What is sigma xi minus x bar? If you don't want to open it up also, it is a measurement of each individual observation separate from x bar. So it is, huh? Huh? This is, what is xi minus x bar for anything? How much does each observation differ from its mean? Summation of all of that. Not squared. It's not squared. How much does each observation differ from overall mean? Standard deviation requires squaring. No, it's much simple, huh? This value, I'm just asking, sorry, maybe I'm confusing you the way I'm asking you. What is sigma xi minus x bar? Okay, let's draw this, okay? x1, x2, x3. let's say this is the mean. Xi minus x bar, xi minus x bar, and xi minus x bar. Sigma of differences with respect to the mean. This is important to get because it's very simple and it will help you understand what is going to happen now. Yes, why? Why is it? It cancels out, right? The definition, sorry, maybe it's this confusing, right? But think of this as a balance scale. X bar is your middle point of where the balance happens. Everything else, if you take the deviation from that X bar, if I sum all of these values, this will be 0. That's what I used previously as well. Does that make sense or not clear? If it is not clear, I can always take the sigma value, and this is sigma x bar. Sigma x bar is what? N times x bar, right? N times x bar means n sigma xi by n. N cancel, sigma xi minus sigma xi 0. Okay, but you don't have to remember and you don't have to do the calculation. If what I are essentially trying to understand, how much does each observation differ from its mean? If you sum it up, it has to be 0, right? Want to hold true for median, but it holds true for mean. Okay, so this term beta naught xy minus xi x bar is, let me write it clearly, otherwise. So this is the term okay. What is this equal to? Expectation of this. Denominator you don't worry about. How do we do this? Quickly. Open up, right? So open up. So expectation okay. First term is equal to, yeah, good. Second term, we'll come to the second term. Last term, why 0? Yes, so this becomes 0 here itself, right? Because this, huh? Say that again. Of epsilon I. Okay, so how does that translate? The intuition is correct, but not fully. Okay, so the reason this becomes 0 is you have an expectation term outside, and overall for each summation, this is epsilon I, this is not epsilon. That's why you cannot, the same logic that you applied here does not apply there. Okay, you'll have to open up. Okay, if you open up, that will be sigma epsilon I xi. If you do sigma epsilon I xi, this you know is 0, and then you take it inside again, and x bar is constant, and e of epsilon I is 0. That's why it's 0. Okay, 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 okay. The when this is 0, this is the only term that's remaining. What is that equal to? Variance. How is the variance? Good. Yeah. This is nothing but sigma xi square minus x bar xi, which you can, if you rewrite this, it's basically the variance of x. This is what we had defined also to be sxx, which is also what is in the denominator. So expectation of beta hat, I should have written this as beta I hat, is beta 1 hat, sorry. This is 1, not I. This is just beta 1. Beta 1 is the true population value of the estimate, and beta 1 hat is our assumed estimate of this beta 1. What we have shown is if we do this experiment again and again, and we take the average slope, which is beta 1 hat, that beta 1 hat will converge to the actual slope, which is beta 1. Okay? Beta 1 is your assumed relationship, right? Beta 1 hat is what you inferred. Expectation of the parameter, which is beta 1, which is the estimated parameter, is equal to the actual parameter. You will write this as, this is estimated. This is okay. The expectation of a parameter being equal to its assumed truth means that this estimate is what's called an unbiased estimate. Okay, this is called unbiased estimation. What is unbiased estimation? If you have a parameter theta, whatever that theta is, if it is equal to its population, if the expectation of this estimated parameter is equal to its population, that's, if this is equal to 0, then that's an, this is an estimator, so this is an unbiased estimator. The technicality of this does not matter, but something that I think you should be aware of. Not all estimates will satisfy this property. It is essentially trying to say that even if I estimate, if I take the estimate of all these in this form, if I take the expectation of all the slope parameters, it is on average equal to the population version. We will come to the sample size. Yes, in this case, the expectation is defined over multiple runs, right? So that is by definition independent in that sense. But there is a variance parameter attached to it, right? We'll come to it in just a bit. Is that what your question was? Like, oh, regardless of the sample size that you're taking. Yes, because this is the repeat of the experiment, not repeat of the samples, right? So even if you take 5 samples and you repeat that experiment again and again, then the estimate of the beta 1 that you will get will converge to its actual parameter. Your question about sample size will just come in, will feature in just now, because how much will it deviate, that is a measure of the standard error, which depends on the sample size. Okay, any questions so far? So this is equal to expectation of sigma epsilon I xi plus sigma epsilon I minus. This, of course, is 0 by definition. This requires a more subtle argument. When we had begin, actually what we had said is the errors are going to be independent, and that independence implies that on average the deviation that there will be no correlation between epsilon I and xi. So it's easier to see it in actually here. This is again measuring on average that if I do a particular deviation, if I do deviate from my particular mean, this error in the long form is going to be perpendicular to xi minus x bar, which is how much it deviates from its mean value, right? And this is independent of, because of that assumption, your overall expectation is 0 for this term. Okay? This comes from, the other way to see this is I could cheat a bit. and I could write my epsilon I as beta 0 minus beta 1 x. This is my xi minus x bar, and if I do expectation over this term and this term are perpendicular to each other, and that's how you get your overall sum to be 0. Any other questions? Okay, so with this we can figure out that the epsilon, expectation of your parameter is equal to beta 1. We could do the same laborious exercise and try to calculate the variance. We'll not do it right now, but what that variance, you can do this, and I'll not ask you, of course, anything like this in the exam. But what you will understand, or what you'll see here, is it's a very interesting relationship that the variance of beta 1 is equal to the sigma square divided by Sxx, which is the amount of deviation that you see in the beta 1 parameter is equal to the overall variation of the model that you had divided by the variation that you see in x, right? And this in a sense is somewhat again relatable, because your slope, the amount of change in this slope will be determined in some sense by how much amount of measurement error that you do, which is what is captured in the numerator, and this will be again be dampened by what you were seeing at the denominator, right? So more variation in beta 1 is an artifact of how much error that you do in your measurement. More is the error, less accurate will be your estimate of your beta 1, and hence the variance of beta 1 will be higher. That comes about to be sigma square by Sxx. Okay, does that make intuitive sense? So that is the derivation. It's not a long derivation actually, but I just don't want to do it again on the board. So very quickly, what it is trying to do is I use the same trick overall, where I wrote beta 1 as xi minus x bar epsilon I by Sxi, right? So this epsilon xi comes from the fact that this is yi minus y bar, and that can be written as your overall epsilon I, right? Okay. So there are two ways to see this. One is when I'm doing this variance operation here, the variance, this term at this point is a constant. There is nothing variable about this particular term. So this entire stuff will come out, and what you will have remaining is just variance of yi, which we had shown last time that if epsilon I follows a normal distribution 0 comma sigma square, your y is also a normal, which means your variance of y is sigma square, and that's essentially what is being plugged in here. Okay, is that clear? It's not very hard to see how that comes about, and that's sigma xi minus x bar square. This term gets squared because this is constant, comes out, and this remains with your sigma square, right? So that's how you get sigma square by Sxx. This is when you square it, that is your Sxx. You get divided by it, so that's how you get 1 Sxx at the bottom. Okay. Okay. So we'll not do it, of course, for beta naught. You can do a similar kind of calculation. It's a bit more work, but the central point there is also that the expectation of beta naught hat is also beta naught, which means that the least square parameter estimate of beta 0 is also unbiased, which means that it is able to measure, or it's a measurement. The expectation of beta naught is equivalent to its true population value. Again, this one is the calculations are on the board. I'll not ask you ever in this exam, but this is for your understanding that where is that stochasticity in measurement coming from. So what we have seen so far are expectation of beta 0, expectation of beta 1, variance of beta 1, and variance of beta 0. One important fact, which is what I asked you in the beginning, was do you think beta 0 and beta 1 is are related or not? And the short answer is that beta 0 and beta 1 are related, and they will have a covariance term contributing towards it, because when you fit a line, the fact that you fit your beta 0 here automatically has an inclination towards meaning what your original slope was. So if you tell me what is your beta 1 in the simple linear regression case, which is your slope, I will be able to infer what is my beta 0, right? If they were not correlated, there would be no way that I would be able to figure out what is this intercept. But the moment I tell you the slope, you will know what is the value of beta naught. How will you know what is the simplest way to know what is your beta naught? What is beta naught generally? The value of y when x is 0. Okay, slightly, yes, that's correct. And what is it trying to capture overall? Some more subtlety, but on the right track. So that is for one observation, right? But you never make one observation, right? So when I have a distribution like this, then I'm saying that this value is beta naught. So that's correct, that when x is 0, this is the value that you get. What is it trying to essentially establish? Okay, okay, yeah, okay, yeah. Okay, why expected value? Hmm. Okay, okay, so correct. So at each point, what you're trying to do is there is again a chance of doing a measurement error here. The goal of beta naught is to capture on an average what is the value of y that you would get if there was no change that was happening at x, which was at 0. So its ideal goal is to capture your y bar, like overall mean estimate of your y when x is 0, right? So this is just a continuation of the last slide. It just puts them in a slightly easier and just a bigger form to capture. So what you get out of these equations of the standard, we'll come back to beta 0, beta 1 in just a bit, but each parameter that we are calculating has a measure of variation that is happening, right? And what I've written here is a term called standard error, and something which all of you have seen. So we have a standard error for beta naught, we have a standard error for beta 1. These are like complicated equations which I'll never ask you. But what I want you to understand is, or what I want you to sort of help me understand is, in this entire exercise, why are we doing so much? Like, what is the reason to, really stretch this so much? Two parameters we estimate we should have moved forward. What is the entire goal, or why are we wasting so much time actually doing this? Hmm? Yeah, no, not independent. That's one thing, of course. But what we are trying to overall do is we are trying to measure whether these are statistically significant, right? And in this course, what we have tried to do is we have tried to fit a model, which is a linear model, but nowhere have we quantified whether this model is overall a good fit or not. Does it actually capture the properties of my data or not? And that's what we are now beginning to do. We will come back to how to actually estimate what are these parameters, but this is a repeated slide. But you have probably seen what is the difference between standard deviation and standard error of the mean. What is standard error and how is it different from standard deviation? And what is the goal of standard errors? Why do we want to quantify something to be a standard error? Yeah, very good, right? So how confident, so the goal of standard error of any parameter is to estimate or to give you a gist of estimate about how close are you to the population estimate of that particular parameter, population mean estimate of that parameter. So for this particular version, again, the slide is repeated, but what it tries to show you is that we are able to calculate standard error of beta 0, beta 1. The equation does not matter. But the reason we are doing all this is we are going to now ask that how close are we to the population estimates of beta 0 and beta 1. And linear regression is nothing but a test of hypothesis. The hypothesis that we began with is that beta 0 and beta 1 is 0. We'll discuss the beta 1 case first. The first hypothesis that we had was there is no association between x and y, and essentially that relies on this model that we are assuming that there is some beta naught plus epsilon that is sufficient to explain. There is some basal mean level, and every observation that you do is hovering around that mean estimate of y. That is the simplest model that will help you explain the observation, and there is nothing about x that ever gets measured. And if this is not clear why this is y bar, we will come to it in just a bit. So under this null, how do we assess whether this is significant or not? The null assumption is beta 1 is equal to 0, and an alternate assumption is beta 1 is not equal to 0. We know the properties of beta 0, beta 1. We know what is its mean value. We know what is its variance or what is its standard error. I don't have to again explain in this class, which is good. How, with this information, how would we go ahead and measure statistically whether beta 1 is significant or not? And you have all seen this in the class. You have all done this implicitly. Okay, why t-test? It measures, why not z-test? Yeah, population variance is not known, right? So you know the properties of beta 1. You know what is its mean. And essentially, in any t statistic, the way you constructed that t statistic was you took some measurement mu. Your hypothesis that was that this is equal to some mu naught and divided by the standard error of, or the standard deviation, depending on how you define it, of that particular parameter was distributed, was known to follow a t distribution. The case here is very simple, that we are saying that beta 1, we have not talked about yet why beta 1 follows a normal distribution, but the logic again should be clear from the same assumption that I could write all of this here as some version of the normal distribution, because my epsilon I is normally distributed. The moment I take this here, I know y was also normally distributed. X is something that you vary. So beta 1 also follows a pseudo normal distribution in some case. We'll not do a formal proof, but hopefully that is clear, right? So with this, we can define a t statistic which will satisfy, which will follow a t distribution. And that's exactly what is done in the case of testing, which you saw, for example, when you looked at the distribution results. But overall, any linear model is actually just a t-test. It's a t-test of whether beta 1 is 0 or is it different from 0, right? So all linear models are nothing but a measurement or in other words, t-test is one of the special cases of a linear regression test where linear regression is a special case of, the linear regression is a special case of t-test where we are testing for a one particular hypothesis is that beta 1 is not equal to 0. The estimate of beta 1 that we what estimate we have is it should be 0. We divide it by the standard error, and this is supposed to follow a t distribution, right, with n minus 2 degrees of freedom overall. That 2 comes because there are now two constraints. One is of the mean, and one is constraint coming from the variance part of it. That's what it is, n minus 2 and not n minus 1. Okay. Does that make sense overall? We'll come back to this in the last section just to flush this out overall. But when you look at the distribution plots, when you look at the output of a linear model, that's what it is essentially trying to do. This is the standard error of your estimate. This is for beta 0. Beta 1, 0 also you can follow the same test. In beta naught, you can actually do a much more targeted test, is that you can say that it should not be 0, but it could be some pre-specified value. That pre-specified value could be the mean, for example. It doesn't matter what that beta 0, 0 is. This is user specified or a pre-specified intercept. This also follows a normal distribution, and hence this follows a t distribution. For each of these quantities, you will derive a standard error for which you can calculate a t value. Now, if we focus on this t value is actually a measure of how tight the correlation is. So if you focus on the t value of your independent variable, the higher this particular t value, the lower will be your p value, and the tighter will be the correlation between x and y, which is what is reported on the bottom here, which is 0.8864. That is square of your correlation coefficient. We will see what is capital R square, and we'll see what is small r square, and so on. But this value here is a measure of correlation coefficient squared between x and y. This number here, which is a t value, and this value here are correlated. They tell you one and the same story. One thing which I skipped in this class is, one way to think about beta 1 is it can be written actually as a function of your correlation coefficient, again after having adjusted for the overall variation between x and y. It's not equal to, there is r, which is correlation coefficient on the x-axis, and covariance or the variance of x on the on the y-axis. And it should be clear how that would come about to be, because SXY is covariance, and this is correlation, and you know the difference, you know the relationship between covariance and correlation. In other words, beta 1 equal to 0 is the same test as your correlation coefficient being 0. In most cases, or in most softwares, beta 1 is what is tested, but in particular you could also test whether this hypothesis holds true or not. It follows the same kind of distribution statistic, which again will not cover it here, but the test that is happening is the same test, whether beta 1 is equal to 0 is equal to doing a correlation coefficient equal to 0 test. Okay, that clear? Okay. Okay, so I've studied confidence interval. So what is a confidence interval? What is you studied confidence interval, right, in the class? Okay, what is a confidence interval? Often when we report the estimate of beta 1, we report this, that it has a certain confidence interval. And of course, there's a formula for which you can calculate, but that is not the goal. So when I did the regression, I got my, so this is my regression, and I got some value of beta 1. I know that this beta 1 could have been different. It could have been this beta 1 hat, or it could be this beta 1 double hat, depending on how many trials of runs that I did for this experiment. So to give you an idea of the repeatability or obtainability of a particular estimate, there is a term, that there's a interval that is constructed. This is called CI. I will call it CI low and CI high. And let's say this is 95% confidence interval. What does it mean? Since you have seen this, we can begin the conversation there. Louder, louder. Okay. Hmm. Same. Anyone else? Confidence interval. Anyone else? Murad? Okay. Anyone else wants to add anything? Why is such a cryptic value to report? It's a cryptic value, right? 95% confidence interval. So let's take an example. Let's say the 95% confidence interval is of beta 1 is minus 2.5 to 2.5. What does it mean? And what can you tell me about the relationship between beta 0, between x and y? 95% confidence interval of beta 1 is minus 2.5 to 2.5. So minus 2.5 and 2.5. Okay, so I could do multiple experiments, right? So first of all, first thing that tells me that if I do 100 such experiments, 95 of these will contain the true population mean, the true population value of it, right? So it's a very bold statement to make, that if I do 100 such experiments, 95 of them on an average will contain the parameter that I'm trying to estimate, which is beta 1. But if you see something like this, which is minus 2.5 to 2.5, what is really, like, what is it trying to tell you overall? From a perspective of whether there is relationship, is there a negative relationship, positive relationship, no relationship? Excluded or included? Okay. But what does it mean, like, overall? From a, what should I tell you? Like, okay, this is the 95% confidence interval of my slope. Then what would you expect your p value to be? Let me ask it the other way around. Hmm? Why? Okay, why less? Why? Why? Okay, so yeah, why? Okay, getting warmer but not full. There is no relationship. Why? Like so if I were to draw, for example, beta 1 follows some t distribution, right? So if I'm given that 95% to be minus 2.5 to 2.5, what does it tell me? That the mean of this is 0 because it's symmetric, and then most of my stuff is encountered in this region. That's 95% confidence interval. Ideally, in an ideal case, you don't want this scenario. You don't want to hover around 0 at all, in fact, because that's what you're testing for. You're testing that how different is it from 0, and this is saying that if I were to repeat this, 95% of these values will lie around that region that you have, right? So if I repeat this again and again, right? So I repeat this again, I get one value of beta here. I repeat this again, I get it here, I get it here, but everything else lies in this regime, which I don't want. and that's what is your estimate of your confidence interval. You want it to be on this regime where 0 is here and you are hovering around somewhere else, where you're saying for sure that I get this estimate mu, but if I do this experiment again, I can hover around in this area. How tight this is tells you how close will you be overall to the population mean, right? So the more tight it is means that you have less variability. Even if you repeat the experiment, you'll be very, very close. But the moment anything contains 0, you are on the wrong side already, because whatever you do, you will land up in the middle of this. Okay, so pay attention to what is the confidence interval, which is not reported explicitly here, but you can of course calculate, because this follows a standard t distribution. So that the confidence interval for beta 1 is given by the estimate minus 2 times standard error on the lower half, and plus 2 times the standard error on the right half, and same thing for beta naught. Okay, so most people will not worry about beta 0, right? They'll say that okay, fine, it's some. Huh? Where did I get the 2 from? The 2 comes from the distribution properties of how much value the entire distribution calculates. So the critical value, which is in this case 2, contains 95% for the t distribution. Okay, this is not z, this is t. Okay, any other questions? Okay, right. So the true value of the slope, the interpretation is that if you were to repeat this experiment again and again, or you do it 100 times, and 95% of those intervals that you calculate, you'll have to calculate the intervals again and again. 95 of them will contain the true value. Okay. So the tighter it is, the tighter these intervals is, you have a higher chance of hitting the true population mean, the true population parameter, and that's what it is often calculated in these settings. Okay. So very simply, if you know, this is a lot of stuff going on in terms of what is happening, but I just wanted to help you visualize overall in regression what is it that we try to do. So y hat is b naught plus beta 1x, doesn't matter what the values of yi are. First thing that you can calculate is the y bar mean, which passes through the mean of your y values. You can calculate multiple things now. Let's assume that this is your xi yi. From this xi yi, I can calculate, this is your xi yi. It says xi, yeah, it does say xi yi. But overall, at this point, sorry, this actually, 1 second, this is slightly incorrect. This value is your xi yi, and what you're getting on the line is xi yi hat. I will fix this. For this estimate, this is the distribution. This is your estimate of how much different your yi is from your yi hat. This is yi hat. This is xi yi. So this is the residual. This is how much does the yi hat differ from the mean. Okay? And overall, you can calculate any value which is yi. You can write it in the form of the fit, which is yi hat, and simply I can add and subtract that yi hat value, which is what it shows. You can do the same thing against the mean. Now I can subtract y bar from each of these equations, and you will get this relationship, and you'll be questioning, why am I talking about this? Because eventually what the model is trying to do is, when you began your regression setting, all you focused on was what was happening in your y-axis, right? And this is why I had posed you the first question. This is your yi. This is y bar. Overall, the overall how much amount of spread you have in your data is quantified by how much does each value differ from its mean, which can be written in the form of this quantity, which is often called, what is it called? It's called TSS, total sum of squares. Okay. Oh, sorry, that's right. Thank you. Yeah, thanks. I'll correct this. Thank you. So here, the next, this is TSS, which is how much amount of variation each of your yi measures from your mean value. There is another measurement that you can do is how much does your residuals vary from the actual measurements, which is the 3-letter word, which is always has interesting connotations, but that's RSS, residual sum of squares. Okay, and then we have an error which we have overall calculated because we fit something. The goal is of any model is to be able to explain the variation in your data. That variation is quantified by this term called total sum of squares, which is simply how much does y vary from its mean value, right? That's in a sense what you're trying to capture, that can I do something different from my mean value, because the mean value is something you can estimate from your data. To do this, you fit a model, and that model is quantifying, this should be RSS and this should be ESS. I will fix it when I put it up online. In the RSS version, what you've done is you have calculated that how much does my yi differ from the estimated value of your how much does your yi vary from the predicted value of yi, and we'll not do the calculation, but again you can do that expansion calculation and you'll find out that in any model the sum of your squares is a function of how much you can explain based on how much is the residual that you can explain, which is not explained by the model. This is what cannot explain by the model, plus what you indeed can explain by the model, which is the expected value of your sum of squares, which is essentially a measure of how much does yi hat differ from y bar, right? Because that is what the model is capturing, and this is what the model is not capturing. Okay. So just to make sure I write this correctly, this is y hat minus square. Sorry. Yeah. How much does the predicted value differ from the expected value of y? That's your ESS. And in overall, you can write this equation as TSS is RSS plus ESS. The reason we are writing this is because we want a measure of how good my model is, right? So the good model ideally should have minimal residual sum of squares, right? If it's a perfect model, you will see that to be 0. One way you can capture this is you can calculate this ratio, which is if I want my model to be maximized, I can ask a very simple question, that how much amount of my variation does my model capture? This is a measure of how much amount of variation can my model explain, but that will be in the absolute sense, which is not interpretable. I divide by TSS on both sides and I get 1 minus RSS by TSS, and this is a measure of what's called coefficient of this is called your R squared value, but it's also equal to R square, the small r square. Sorry, that slide has gone missing. Sorry, they are a bit out of place. 1 second. Sorry, I think I hit that slide. Should be there actually. Okay. Anyway, I will add it. You will see that if you actually expand this and calculate this, this is nothing but equal to correlation of xy squared. This is only true in the case of a simple linear regression, which means you have only one x and one y. So r square, which is capital R, this is called capital R square, is equal to small r square, which is equal to nothing but, actually don't need a slide for this, this is what I wanted to say. This only happens if you have a simple linear regression case, which is 1y, which is usually true, and 1x. It is not true for higher order case, which will come, which we'll start covering later in the class, which is multiple linear regression. Okay, so in a sense, what I want you to remember is linear regression is nothing but just a model for t-test. Imagine you had this model, right, which is y is equal to epsilon, and the second model was beta 0 plus epsilon. How would you formulate a test for this? You have two models, y is equal to epsilon, and you want to test against the alternate model, which is beta naught plus epsilon. How will you test which model is correct? Or in other words, how will you test for the significance of beta naught? How will you test for the significance of beta naught? We'll just do this. We don't have to do it formally, but and then that's when we'll end. Any ideas? Simple model, right? Y is nothing but epsilon, which is, and y is same thing. And I want to test this idea that beta naught is equal to mu naught. How will I do a test for this? What do we know about beta naught? Okay, this is just algebra. Now my question is beta naught equal to mu naught? That test, how do we do? That's a hypothesis, right? Forget about the other model, but this test, how do we do? I want to test is, this is my new null, let's say. How do I prove or disprove this, or accept or reject this? Mu naught is specified. You can assume that that is known. Okay, we make a t-test. Good. And effectively, what have you tested for? You have tested for whether that slope, the intercept, is that significantly different from a pre-specified value, which could be 0 as well, right? So essentially here, this is nothing which your linear model is trying to do. At each step, it is just running a t-test and asking the value for whether this model should you choose this model versus this. This is the example for your null for your intercept. You could repeat the same example for your slope. It is essentially just a t-test, right? So any linear model is a t-test for its coefficients. If they are significant, the relationship holds. If it does not, that particular relationship, which is linear relationship, does not hold. Okay. Any questions about this? I see a lot of confused faces, just because probably we did a lot of there's a lot of back and forth, but happy to explain anything which was not clear. Okay, so next time when we come back, after your assignments will be released this weekend, when you come back, we will very quickly talk about how do we diagnose the fit, whether it's a good fit or a bad fit, and then we will move on to doing other forms of regression. Okay, great. Thank you.